So the 2010 paper, question 2, we're on DC electricity, and this is NCEA Physics Level 2. Frank is out camping. He's just done just one 12-volt battery with him. He connects various low voltage devices to his battery as shown on the diagram. So the resistors, I guess, are meant to represent the low voltage devices. Calculate the effective resistance of the circuit. So what that means is we're trying to find the total resistance of the circuit. And this is a little bit like maths when you've got brackets everywhere. You have to add up the bits. I don't know if that bell's coming through, but I'll just wait till it stops because it's in my ears and my brain. Anyway, okay, it's finished. So as I said, you have to add these up, and sort of like the way that you work your way with brackets, there's a particular order that you have to do. So the order in this case is that we would have to add these two together first, work out what the resistance of that is, which is easy because it's 4 plus 2 because it's a series connection, which gives us effective resistance of 6.0 ohms. Then we've got to add the parallel section here, which is going to be 1 over 6 plus 1 over 5. Let's do that, 1 over 6 plus 1 over 5. And then when you work that out, you take the inverse of that. And then once you've got that value, which is about 2.73, according to the marking schedule. I am cheating, but I've got to be fast so my video is not too long. So that's 2.73 ohms. Then you just add that to the series section, so 2.73 plus 3.0, which gives you 5.73. And if we're rounding to two significant figures, because everything's got two significant figures. We'd be multiplying, dividing, and adding and subtracting, but two significant figures for everything. So 2 for the final, 5.7 units ohms. B, calculate the current through the 3 ohm resistor. Okay, trick for this one is knowing that the current through the 3 ohm resistor is the current through the entire circuit. So we've got the total circuit resistance. We can use the total voltage, 12 volts, to find the total current which will be going through there. So it's I equals V over R. Voltage is 12 volts. Total resistance is 5.73 because you use your unrounded value, and that gives you 2.09 amps. And again 2SF because voltage is 2SF, and we really should round like our resistance effectively is to 2SF because of our earlier readings. We just use the unrounded value for our calculations. Anyway, that gives us 2.1 amps. I don't think that'd penalise you at this level if you were out by say 0.0 whatever, 1 or 2, or if yeah, anyway, moving on. Also, that question relates to if you had a different answer for the total circuit resistance, they would allow that. Now, getting a bit more trickier, calculate the current through the 5 ohm resistor. So, what we need to know to find the current through the 5 ohm resistor is what the voltage across the parallel section will be. That's the easiest way to do it. If we know the voltage across the parallel section, then we can use I equals V over R, using just the voltage and the resistance for that that one resistor. So we'll do that. We know that there's 2.1 amps travelling through the circuit, so we can find the voltage across the 3 ohm, which is annoying having to go back and forward, but see the I'll explain it. We can do V equals IR using the total circuit current and the 3 ohm resistance to find the voltage across the 3 ohm. Take that away, that voltage away from the 12 volts will give us the voltage across there. Then we can use I equals V over R to find the current through the 5 ohm resistor. Okay, so voltage across there is current 2.09 using unrounded times the resistance, which is 3 ohms, 3.0. Gives us a voltage of 6.27, which means there's 12 minus 6.27 volts, which is, so this is the voltage across the 5 ohm, or the parallel section, is this is 12 minus 6.27, 5.73, is that right? Yep. Oh, that's interesting, because it's the same as the resistance calculated in parallel. I wonder if there's a trick in that. Interesting. So that's there, and we don't know the current. We're trying to find the current. We know the resistance because it's the resistor. It's 5 ohm resistor. So I equals V over R, 5.73 over the 5 ohms, 5.0. Final answer to two significant figures is a current of 1.0 or 1.15 or 1.2 excuse me, amps. Okay, there's other ways you could do that as well. You could use the total circuit current and work out how it splits up according to the proportion that 5 ohm section is of that. So total circuit current, you can work that one out. You can work that one out. I've got to move on. This is a long question. As it grows dark, Frank replaces all the devices with lamps of resistances similar to those of his low voltage devices at that temperature. Okay, that's convenient because lamps don't hold a constant resistance, but we'll stick with that. Discuss which of the two lamps, oh, this is going to be tricky. 3 ohm lamp, okay, so the 3 ohm lamp, where's that? This one here, or this one here, this is the 3 ohm lamp. Or the 4 ohm lamp in the above circuit will be brighter. There's the 4 ohm lamp. You may use calculations to support your answer. Okay. So one way you could do the calculations is you could find the power, which is the current times the voltage for each of those lamps. That's one way to do it. Depending how detailed you want to get, and there's some variations of that as well, because V equals I times R, you can have a power of I squared R, and it can also be V squared over R. Since we sort of already have the current values, so I would use this I squared R, because we know the current going through here is 1.15 amps, and the current going through the 3 ohm resistor is, what was it, 2.09. So that means the current going through the 4 ohm resistor would have to be the remainder of, because remember the current splits up, part goes here, part goes here, so that would leave around about 0.95 amps going through there. So I'll do that right, 95 plus 1.15 is 2.2, no, 0.85. So it's 0.85 going through there. So let's just do those calculations, because as I said, the brightness is related to the power, and the more power, the more energy is being converted to light and heat in this case, and we would assume that the amount of light and the amount of heat is kind of consistent across all the lamps. So therefore we can work out the brightness. Let's go. So I squared R. So for the 3 ohm, you would have 2.1 squared times R is 3, which equals whatever it equals. 2 2s are 4, 3s are 12, it's approximately 12 watts, because power is joules per second. And then for the 4 ohm one, you've got 0.85 squared times by 4, which is going to be much lower than that. 0.85 squared, even if we round that up to 1, 1's a 1, times 4 is 4 watts, it's going to be less than 4 watts. So from this we could work out that the 3 ohm lamp is going to be brighter. And something was bugging me about this. I think it was, yeah, this is actually 0.95. That's still not going to significantly alter our results. Sometimes your intuition just niggles away. It takes a bit of practice to get used to listening to it. But anyway, so answering that question, it's not enough to do the calculations. You have to then say the 3 ohm is brighter, and then just explain that this is to do with power. Power is equivalent to brightness, and then power is current times voltage, and then you carry on and do the calculations from there. Anyway, Harry connects a diode and a resistor separately to the variable voltage supply and studies the voltage current characteristics of each of them. He displays his findings on the graph as shown below. Okay, so there's the diode connected, there's the resistor connected, the variable voltage supply, because it's got the arrow through, and they've adjusted the voltage, increasing the voltage and measuring the current, although there's no ammeter in the circuit diagram. E. Using the information from the graph, discuss the effect of voltage on the current for each of the components and explain how the shape of the graph supports your answer. Include ideas of resistance for each component in your answer. Okay, remember from Ohm's law, R equals V over I. So this one here, they don't label it, but this is the resistor, so you're expected to know that. And that's got a very consistent, so resistors are consistent increase, because we're discussing the effective voltage on the current, consistent increase in current as voltage increases. Okay, so the corresponding version for diode would be, it's an inconsistent increase in current as voltage increases. In fact, as voltage increases, you have a very small increase in current, and then all of a sudden it hits a threshold voltage and goes huge current. So you'll describe that as well. I'm not writing it down because the video is already getting long. And now explaining how the shape, well, we would say you can see there's two things you talk about. You could just talk about the straight line for the resistor, so straight line showing voltage and current increasing together evenly. You could also talk about the gradient. So the gradient is the resistance, and that is constant, which means constant current. Now for the diode, you can talk about the gradient is not straight. In fact, it increases. The gradient decreases as voltage increases. Once you get over that threshold voltage, and since you're decreasing resistance, current will increase as well. Okay, you can explain all of that in quite a bit of detail if you really want. And that's the full end of this question. And I've done that really fast in this 12 minutes. Well done for listening. Hope you check out other videos in the Physics Lounge as well.